There we go. Oh.
Okay. Paulina,
Yeah.
you're going to take over.
Okay, so are we good? Did you already switch off?
You should be able to, actually,
cool.
share.
Okay, so now we're going to cover module 11, which is quantum numbers. Let me share my screen. All right, so who can tell me what the principal quantum number is? What do we use to signify that, to symbolize that?
N.
And what does it mean? Okay, why is it yellow?
Like the energy level or the shell your electron is in?
Yes, so it means energy level, right? Okay. Okay, sorry for that extra E. And then L, what is L?
Isn't it the shape of the
angular momentum?
Angular momentum. Okay, so angular momentum. It is the shape, right? The shape of what?
orbital?
Shape of the orbital. Okay, and what shapes can we have?
S and S, P, D, F.
Yes, S, P, D, and F. So if we have S, what is it going to look like?
This is 0. Oh, okay.
Yes, the angular momentum number will be 0, but what is it going to look like?
Like a ball.
Like a sphere, yeah. Okay, cool. And then we can have P, D, and F. So can anyone tell me what P will look like? We said this was gonna be. Okay, so it's gonna look kind of like a dumbbell, like an infinity sign. And then this is gonna be important when we get into hybridization. So just keep this in mind. Okay, and then D is gonna look like 2 dumbbells together. And what will be the angular momentum number for D? Three, right?
You're right.
Okay.
Oh, okay.
Okay, and now we have M sub L. So what is M sub L?
The wave of spin.
Okay, yeah, so it's the magnetic quantum number, right? And is that the spin? Or what does it describe?
I have a question. Isn't it S 0 and P 1?
Yes, you're absolutely right. I skipped one. Sorry. Good job. Who was that?
Me, Hazel.
Good job. Yeah, I skipped one. Sorry. Okay, F is 3. Yeah. Good job. Okay, so we have the magnetic quantum number. So does that, I think someone said spin, but is that the spin?
I thought it was the orientation.
It's the orientation, yeah,
Yes.
sorry.
Good job. Orientation. And now we have M sub S, which is the spin. And we call it electron spin. So I'm just going to put spin. So you can remember that with the S, right? Okay. So when you think of these, I know it's kind of conceptual and I had a hard time learning it when I was going through. So just think of like, well, first of all, how do we write, conventionally, how do we write out the quantum numbers? The question asked you, what are the quantum numbers for lithium? We would write, which one goes first?
The energy level goes first, the N,
Mhm.
and then L.
Exactly how we have it, right?
Yep.
We separate them with commas and we put them in parentheses. So I like to think of this as kind of like an electron address. Like you're estimating where they are around that atom. Okay, so I know it's kind of weird and maybe this will help you. So it's kind of like an address, right? If you give someone your address, you have numbers and you have letters, but you have numbers, right? Okay, so let's do some practice. Okay, and one thing to note. So what rule do we have associated with quantum numbers? Anyone? Or what principle?
Isn't there the Pauli exclusion principle?
Pauli exclusion, right? And what does that tell us?
No two electrons in an atom can have the same values for all the quantum numbers.
Exactly. So you can't live in the same house as your friend, right? I mean, I guess you could, but you both have different addresses, right? So kind of think of it that way. No two electrons are going to have the same, exact same quantum numbers. Sorry, what was that?
Can I cut in real quick?
Yes, go ahead.
I like to tell my students they're like social security numbers because I am never going to have the exact same social security number as anybody else, at least not while we're both living, right? And so because of the Pauli exclusion principle, no two electrons can have the exact same quantum numbers. So just like I can't have the exact same social security number as you, no two electrons can have the same quantum numbers. Okay, I'm done.
Exactly. Thank you, Sophia. Okay, I'm pulling up some of my questions. Just give me 1 second. All right, so let's go ahead and try these. Share my screen again. Okay. So we want to write the complete set of quantum numbers that represent the valence electrons for the following numbers. Okay, so let's start with helium. Why isn't it? Sorry guys, I'm literally the worst with technology. Okay. There we go. Okay. So let's start with helium. What is going to be the N value, the N quantum number for helium? How do we determine that?
Well, it's 1 because it's on the first row of the periodic table.
Exactly. N is easy, right? Because you just go down the periodic table. So if it's in the first row, we know that the N quantum number is going to be 1. And next we have which quantum number?
0.
Okay, yeah, it's 0, but what's the name of this quantum number? Just so we can practice.
L.
Okay,
Is that what
cool.
you're asking, Paulina?
Yes, thank you. And next we have actually
M sub L.
M sub L. And how do we determine that one? So M sub L is based off of which previous quantum number that we already had?
L.
L. So M sub L, let me write it up here. M sub L has to be between, how is it based on L?
It has to be between negative L and positive L.
Exactly. So negative L to L. But in this case, our L is just 0, so M sub L has to be 0, right?
Yep.
Okay. And next we have M sub S, so that is the spin. So electrons can have how many spins?
2.
2. Positive and negative, what value?
1/2.
Yes. So we base this off of our orbital diagram, right? So what does our orbital diagram look like for helium? So this is the 1s, right?
Right.
And how do we fill this in?
You do the positive up arrow first,
Mm-hmm.
and then the down arrow next.
Yes, and based on the spin, we always go off of the last one we draw, right? So this one is going to be -1/2. Okay, cool. So let's do, okay, I'll do one more, and then Diego, if you want to take over. Sound good? Okay, so let's try nickel. Nickel is in which row?
4.
4. Okay. Anyone else want to give it a shot? For L?
Hint, hint, it might help if you guys do the electron configuration on your end.
Can I jump in real quick?
Yes, go ahead.
So like obviously like we figured out that like n it's based off the rows, but I don't know if we like went in detail with this, but like yeah, a really simple way to figure out L is well, since we know that S it has 2 electrons, so we know that the first 2 columns are going to be S. So those first 2 will always have one of 0, and then P we already said is 1, and P has 6 electrons in it. So the far right ones will always be L will always equal 1, and then for the ones in the middle, where it's D that has 10 electrons, those will always be 2, and then F will always be 3.
Yeah, I'm gonna pull up a periodic table because I wanted to say that, but it doesn't. I feel like it's helpful if we see it. So let me just really quick.
Oh, yeah. Because like if you always have a periodic table in front of you, I think that it makes this whole module a lot easier to understand.
Mhm. Okay, so okay. So if you're looking at the periodic table, what he was saying was, okay, so group 1 and group 2, we know this is the s orbital, right? So these are going to have an L value of 0. And then let me do it a different color. This is so hard. I'm like not an arts major, clearly. Okay. And then so are these your metals or non-metals?
Non-metals.
Non-metals. So your non-metals are going to have L value of 1. And then your transition metals,
That's
everything
your
over here, I'm just going to go like this. So our transition metals are going to have an L value of 2. And then this block down here, what color? What L value will these have?
3.
3. Cool. Okay, so is that like better for you guys to visualize? Yeah.
Yes.
Okay. Cool. Okay, I'm gonna stop sharing. All right. Diego, did you want me to go through one more?
No,
Did
I'll
I
go ahead and
finish the one I
cover.
was going through? I just realized I didn't even finish it.
It's okay.
Okay.
So I'll go ahead and quick run through of electron configuration. So a lot of you guys may be used to using your periodic table, right? I'm pretty sure that's the method everyone is using, where you identify which block you're in, and then you count up all your electrons.
Well, there is an easier method that I wanted to share with you guys. So what are we doing basically with electron configuration? What are we counting up?
Aren't we counting the valence electrons?
Not completely. We're including those. We have the valence electrons, and then what else do we have?
The electrons.
Yeah, we're counting up basically all of our electrons. Configuration. So electron configuration, here we are counting up electrons. Okay, so for those of you who may still be struggling with understanding the periodic table, this might be a method you might prefer. So it takes a little bit to set up because you have to draw it, but once you draw it and once you understand it, it'll help a lot. So how many levels do I have for S?
2.
No, not electrons. How many levels we have? Energy levels.
Oh.
7.
7. We have 7. Sorry, I don't have my chat open. I should probably have it open. Yes, we have 7. 7 levels. So 3s, 4s, 5s, 6s, 7s. Okay, and then what level does the P block start at?
2p.
Starts at 2p. And then up to what number do I go for my
So 7.
7.
7? So 3p, 4p, 5p, 6p, and 7p. What level does D block start at?
At the number less than the what it says on the S.
I think you meant P.
It will be 3.
Yeah, it'll start at 3D.
Were you asking for D? Oh, okay.
Yeah, sorry, yes, for 3D. No, it's okay, no worries. So we have 3D, then we have 4D, 5D, 6D, and then for F, what level do we start at?
Or F.
We start at 4F, and then we only have 5F. Okay, so here you could write all your exponents, but I'm gonna assume that you all know. How many electrons can our S block hold?
2.
2 electrons. Our P block?
6.
6,
Our D block?
10.
10,
And our F block?
14.
14.
14. Nice. 6, 6, 6, 6, 6, 6. D is 10, 10, 10, 10, and 14, 14. Okay. Now that I wrote up all my electrons, let me show you how you use this graph real quick. The way you use this graph is you start off from the top right corner and diagonally downward. And you always want to go diagonally downward. So I'm just going to make the lines real quick. That way you guys sort of, oh dear, 4F, 4P, 5S. Okay, it's a lot of lines, I know. Don't worry, we're not going to get as deep as that. So let's go ahead and run through an example. So let's go ahead and do oxygen first. Oxygen is a pretty simple molecule. How many electrons does oxygen have?
8.
It has 8 electrons. Okay, so we want to make sure that we count up to 8. Okay, so 1s2. How many electrons do I have there?
2.
2.
2s2.
Another 2.
2p6. How many electrons?
I give you 6.
And then what does this add up to?
10.
10.
8.
This adds up to 10, but how many electrons do I need?
8.
8.
No,
So it would be a 2p.
So it will be 4.
Yes, 2p4. Why would it be 4? How many electrons do I need to subtract from the last one?
2.
10, 2.
I need to subtract 2. So instead of it being 6, it is now 4. And there we go. That is our correct electron configuration for oxygen. Is there any questions on how this method works? You guys want to do another example?
Yes.
Okay. No worries. Okay, let me go ahead and erase that, those arrows. Okay, and then what about, let's do chlorine. How many electrons does chlorine have?
17.
17 electrons. Okay, so how do I start it off?
1 is 1. And then
2s2. 2p6. And then 3s2. And it will be 3p. 6.
3p5.
3p5.
I didn't want to make it red. Give me one quick moment. It erases when it's not supposed to. Okay, so I added 2, 2, 2, and 5. And then how many electrons is that right there that I just wrote down?
17.
17 electrons. So this is correct. And that is your electron configuration. All right, let's try one with D. Someone give me an example.
Can you do a transition metal?
Let's do cobalt. I like cobalt.
Yeah, sure. Cobalt works. So I'm going to go ahead and erase oxygen real quick. That way we have space. Okay. So cobalt, how many electrons do I have?
7.
27.
Yes, 27. 27 electrons. And then, so how do I start it off?
Well, 1 is 1.
Mhm.
And then 2s2. 2p6. And then 3s2. And then 3p6. Then 4s2. Then 4d9.
Is it 87?
I mean 7, yeah.
3d7. There you go. And if I add up all those numbers that I just wrote down, all those electrons, what number do you guys get?
27.
27. That's how you can always check if your electron configuration is correct, if you have the exact same number of electrons.
Do you want to try copper?
Sure. An exception.
I have a question. Can we also like put like a noble gas instead of like writing it all? Like let's
Yes.
say a noble gas before and then.
Yeah, sorry, I was torturing you guys and making you write the long version. Okay, if we're gonna do the for copper, how many electrons does it have, first of all?
29.
29 electrons. Okay, and then if I'm gonna do the shortcut method, what is the nearest? What is the previous noble gas before copper?
Argon.
Argon. And argon, how many electrons does it have?
18.
Okay, 18. So we already started off with 18. So argon goes up to 3p6. So right now we're at 3p6. So we just covered all this. And then, so how do I continue for copper?
First 2. And then 3d9.
Well, what's special about copper? What doesn't copper like?
It's unstable in the 3D show.
It's unstable. It has 9. It's very close to having a full subshell. So what does copper do?
It goes from 4s1, 3d10.
Yes. So what copper does is that it pulls 1 electron and puts it in its d subshell. So it's 4s1, 3d10. And
So,
then, sorry.
And then 4s1, right?
It would be yes, it'd be 3d10 for s1. We still get 29 electrons at the end.
Yes.
You still get 29 electrons. So that's how we know this is, or we have the correct amount of electrons, and we made sure that the exception was identified.
I'm gonna jump in really quick. So, what's special about elements that are in the same column? Anyone want to try? Okay, so if we had silver, so silver is right under copper, right? It would have a similar electron configuration to copper. So everything in that column with copper and also with chromium, it'll follow this same exception. So it's not just those two elements, or it's not just copper, it's everything in those groups, okay?
So can someone tell me what some of our other exceptions are? What's some of the exceptions we have?
Hint, hint, where have we found all these other exceptions?
So we have copper.
Well, there's chromium. Lena just said it.
Silver.
And then silver.
Yeah, silver.
And then whatever that one below chromium's called, MO.
Mobium, I believe, right?
Is it palladium or something like that? Oh no, that one's next to it.
No, yes. All right. How does everyone feel about electron configuration? Do you guys prefer this method, or do you guys prefer the the periodic table?
This one, I used this one, and it was easier this way.
This one's much easier, yeah.
Yes, I definitely prefer this method. Thank you. Mostly because it's easier to count up the electrons. You don't have to deal with traversing through your periodic table. Would you guys like to cover the periodic table, or would you just like to move on? Examples.
Remember, guys, whatever works for you to understand it, it's valid. So either the periodic table or what Diego just showed you guys is perfectly good and valid for you guys to get it.
Or, but maybe for the sake of the recording, we can cover the periodic table just once.
Let me go ahead and stop sharing and screen share again. Okay, so here we have the periodic table. This is my interactive periodic table. It's fancy. It blows up. So for our periodic table, typically the way I like to state it as is basically like run your finger along the periodic table, counting up your electrons. So, yep, sorry, there's someone in chat. Yes. So starting off, which is my S block? Pretty sure it's pretty redundant at this point, but which is my S block? Yes, the first two.
Isn't it the first two columns? Yeah.
Yes, the first two columns. So this is my S block, my P block. First of all, what happens to helium? Where does helium go?
Next to hydrogen.
It gets moved over here with hydrogen. So helium gets moved over here. And then my P block, what is my P block at?
That's 6 columns.
It's the 6 columns. This is P. And then my D block?
It has the metalloids in between. Or sorry, the transition in between.
Yes. So this is my D block. And then my F block.
Is those 2 rows at the bottom.
This is my F block. Typically, you guys won't be asked to go all the way down to F. That's a bit extreme. Typically, you guys will stay around this area. Okay, so start off easy and then move into slightly harder questions. So if I wanted to do, let's say, the electron configuration of aluminum, how many electrons does aluminum have, first of all? 13 electrons. Okay. And then if I were to follow along, let's say if I were just to follow along with my finger, how would I start it off?
Well, you start with the hydrogen and helium, which is 1s2.
1s2.
And then you go down to lithium and beryllium, which is 2s2. And then you continue to the P, which is 2p6. And then you go down to sodium and magnesium, and which is 3s2. And then you stop at aluminum, which is 3p1.
And then how do I check if my electron configuration is correct?
You can add the numbers, I guess.
Yeah, you can add your exponents. So have 2 plus 2 plus 6 plus 2 plus 1. Sorry, just something in the chat. Okay, so does this give me 13?
Yes.
Yes, it gives me 13. That is correct. This is correct, and there's not an exception, so we're Gucci. Okay, let's go ahead and do one with the transition metal. So if I'm going to do one with my transition metals, I don't know why. Oh, sorry, it's because it glitches out sometimes. So I'm going to go ahead and clear it. Ah, shoot, I didn't want to clear all of it. Okay. All right, that's S. The hydrogen 1, 2, 3, 4, 5, 6, 7. D and then F. Okay, let's do nickel for now, and then we'll do silver later. So, how would we start? First of all, how many electrons does nickel have?
28. No, yeah, 28.
28. So we need to make sure I end up with 28. So if I follow along with my finger, how would it go? Or would you guys? Oh, go ahead.
I prefer the shortcut where you pick the noble gas before it.
Yeah, I was about to say, let's do the shortcut method. That way I don't have to write so much. So which is the noble gas before?
Argon.
Argon. And argon has 18 electrons. And then how would I continue? So I have here up to here for now.
You go to potassium and calcium, and that's a 4s2.
4s2.
And then the next one would be a 3d8.
Yes, 3d8. So 1, 2, 3, 4, 5, 6, 7. Did I count wrong? I think I counted wrong. Sorry. Yeah. Sorry. Okay. And then how do I check that my electron configuration is correct?
You add your
So argon has 18 plus 2 plus 8. Does this give me 28?
Yes.
28 electrons. And is this an exception?
No.
No, this is not an exception. So this is, in fact, our correct electron configuration. Nice. Okay, so let's go ahead. I'm going to leave it there for a bit. Remember, we are still recording the sessions, so don't worry. Go ahead and check chat. What are the exceptions again? Can someone tell me what the exceptions are?
So it's chromium, copper, and then MO, and silver.
Yeah, so we have chromium, copper, MO, and silver. I believe gold is also one of them. So anything under this column and anything under this column.
Okay, thanks.
No worries. Okay.
So let's go ahead.
Sure,
about
go
the exceptions. Why are they exceptions in specific areas? I don't know if you explain.
Can one of the peer
Yeah, I
leaders
can
explain?
take it. I'll explain this. Sorry,
You know,
go
you
too.
go, Paulina, don't worry.
Okay, so essentially, when we did copper, we saw that it was 4s2 3d9, right? So 3d9 is almost full, right? Like it's just missing one. So if it takes one from the 4s subshell, it makes that one, it makes the 3d completely full, so it's happy, it's stable, and it makes the 4s exactly half full. And that's much more stable than 4s being completely full and 3d being almost full. So it likes to be either completely full or exactly half full. And if you can tell, like there's a pattern. So chromium, why do we think it's chromium and copper? Why do we think it's those columns that are the exceptions? So we know why it's the copper column because the 3D is almost completely full, but the chromium, the 3D is almost half full, right? So the last one for chromium would be 3D4, right? But if we take one from the 4s, we make it 3d5 and we make both of them half full. So 4s1, thank you for drawing that out. 4s1 and then 3d5. So both of them would be exactly half full, and that's much more stable than 3D being not half full or not completely full.
Okay, and that would apply to tungsten and
Suborgium. Yeah.
That one.
Yes, because it would follow the rule for the column.
Okay, cool.
No worries. Okay. Actually, I just realized this. Sorry, I'm going to erase this. Disturbs me. But like, if I click on here, it tells me the electron configuration or how many electrons it has per subshell. Cool. Okay. Let's do silver. We're saying silver is next. So Ag. First of all, how many electrons?
47.
47. Okay, at the 47 electrons at the end of this. And then what is the last known noble gas?
Krypton.
Krypton, yes. Yes, it's krypton. Remember, it's our last electron, not the one that's ahead. So krypton, and then krypton has 36 electrons, sorry. And then, so how would I continue it afterwards?
You go to rubidium and strontium, so that makes it a 5s2.
5s2. And then how do I continue it off?
So the next one would be a 4d9. Yeah.
4d9. Okay, but what's special about silver?
That it's gonna attract one electron from the 5s2.
We're doing silver. Yes. Yes, we're gonna take one electron from here so it can have a full subshell. So what would be my Lou electron configuration?
So it'd be krypton 5s1 and then 4d10.
5s1 and 4d10. And then does this add up to 47 electrons?
Yes, it does.
Yes.
Yes, 47 electrons. This is correct. There we go. All right. Nice, guys.
I have a question.
Sure, go ahead.
How do ions work?
Oh, yes. How do ions work? How do we do ions? So let's do a silver ion then, in that case. I'm going to go ahead and erase this for now. So let's do silver +1. How many electrons would silver +1 have then?
It would lose an electron.
So I would have 46 electrons now. So we're still doing the whole shortcut method. So we still have krypton. So that's 36. And then how would I continue writing?
That would be still 5s1, right?
Yeah, so well, let's do 5s2 for now.
Okay.
So 5s2.
And then 4d8.
Yes, 4d8. Okay. And it being an exception, what do you think silver does in order to have its electrons full?
It grabs an electron from the 5s2 again.
Mm-hmm. But would it grab one or both?
It'll grab, I think, 2, right?
Mm-hmm. It would grab both. It would grab both electrons. Yes. So instead of it being 5s2, now we have 36, 4d10. Is everyone clear on what happened? Sorry. Okay. Do you guys want to continue doing ions? Or
Okay, I think we should do an anion instead.
anion. Okay, sure. So let me go ahead and clear it. Okay, so for an anion, typically they're nonmetals. So let's do bromine as an example. So bromine. So how many electrons would bromine anion have?
36, right?
36 electrons. And if I'm doing the shortcut method?
So that's argon.
Argon, which has 18.
Argon. And then the 4s2. And then the 3d10. And 3p6.
Not 3p.
I mean 3p7. I mean.
You're right about your exponents the first time. It's your energy shell.
Isn't it 4p6?
Yes, it's 4p6.
Oh yeah, my bad.
Yes, 4p6. What is this isoelectronic to?
Krypton.
Yes, it's isoelectronic to krypton. Nice. Do you guys have any questions?
I think we forgot to mention like how ions come into play with the periodic trends. I don't know if you want to talk about that.
I think we did. I think Jonathan covered it.
Did we?
Yeah.
I forgot. Okay, just kidding.
He talked about how he would increase the nuclear effective charge, I think.
Oh yeah.
Okay, let's go ahead and do electron configuration and quantum numbers then. Does any of the other pre-leaders, do you guys want to give it a shot? I don't want to be talking that much.
What's next?
Could you repeat that?
No, if you guys would like to go over problems with them.
Yeah,
Electron configuration and quantum numbers.
Students need more problems. Students, do you need more problems, or do you think you're fine with this?
Guys, good? No comments?
I'm good.
Complaints? Well, you're good, but I always tell my students, don't let others speak for you. So
How about the
speak
other
now or
10?
forever hold your peace.
Another one.
Another one.
One
Okay.
more. All right.
Does someone want to do it though? Or do you guys want me to do it?
Well, you could do it, but I can choose it if you want.
Sure. Go ahead and tell me which one.
It has 49 protons. Ha 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 ha.
Indium? Okay. All right, we'll do indium. We'll do the electron configuration, and then we'll also do quantum numbers. That way you guys can also review quantum numbers. So for electron configuration, well, I already have at 49 electrons. We're doing shortcuts, so how would I start it off?
Krypton.
Krypton. 36. Thank you, Brianna. And then how do I continue it?
5s2.
5s2. I wrote that really big. So 5s2.
4d10.
4d10.
And then 5p1.
Yes, 5p1. Okay. And then, so if I want to do my electron configuration, which N, L, ML, and then MS, what pair of electrons do I base it on?
5? Wait.
What electron pairs do I base my answers on? Sorry, let me check chat.
No, that's
You
fine.
guys-
Chat is just me.
Okay.
Are you talking about the last electron?
Yes. We base it on our last electron pairs. So we'll base it on 5p. And then, so what will be our n?
5.
N would be 5.
L?
1.
1.
Yes, it would be 1. If you guys remember, it would be 0, 1, 2, 3. I recommend drawing or writing down this little graph. It helps a lot. P, D, F, G, and H. We don't use G and H much. ML. What do I?
It would be from -1 to 1, right?
It'd be
It would be
negative
1.
0, 1. Before you
1.
get ahead, how many boxes do I draw for P? How many orbital diagrams?
3.
I have 3. And then if I were to fill my electrons, how many electrons would I fill?
Just 1.
1.
And what orientation would it be?
Positive.
Positive. So it would be -1 and then +1/2. There you go. Is there any questions?
I have a question for the students. Which element is more electronegative, gallium or indium? Or
gallium or indium?
And why?
Oof.
What's the trend, you guys?
I can tell you which one's more electronegative, but I can't tell you why.
Gallium is more electronegative.
Perfect.
Why?
Ooh, that's where
Isn't it because
someone's
I'm
gonna
not
have to help me on that one.
Thorium's king.
I'll give you a hint. It has to do with the atomic radius.
Yeah.
That too. I was looking for a simple answer, but if we want to go scientific, totally.
What's the trend? What's the trend, guys? What's the trend?
It increases as it goes up.
Right. Exactly. It increases.
So why is gallium more electronegative than indium?
Because it's more up than indium.
Exactly. Woo.
Wait.
Ooh, Jerry, do you want to explain it or me? No, you go.
Wait.
Go.
Okay. Wait. Actually, there's one more that I want to do just to see, like, your guys' thought process behind electronegativity.
Go for it, Jerry.
So, which one do you guys think is more electronegative, nitrogen or bromine?
I would say nitrogen.
Okay,
I can see. It's
Don't
basically
spoil it,
the same
Diego.
thing as. Oh, gosh.
No, it's not quite. But there's like one specific reason for why one's more electronegative than the other. But I just want to see if everyone can guess it.
Nitrogen?
The 2 elements, please.
Nitrogen and bromine.
Okay.
Oh, bromine.
Okay, I got a bromine. Okay, well, since apparently it shows nitrogen, I'll ask why'd you choose bromine?
Bromine because it would be so since it's smaller, has more protons, it draws the electrons in tighter. So it has a higher, since there's more protons, there's a higher it's has a more of a draw towards the electrons.
Well, your thought process is kind of in the right direction, but it isn't at the same time. So, okay, what I mean by that is that when you were thinking smaller is more electronegative, that's right. But the reason why bromine's more electronegative than nitrogen is because it's a halogen. And we know that all halogens need one more electron in order for it to be full. So since it only needs that one more electron, it's a lot more likely to be able to pull those electrons. Like, it may be more electronegative than nitrogen, but not by a lot. That's but like all of those are more electronegative. That's why fluorine's the most electronegative, and then chlorine's more electronegative than oxygen, and so on and so forth. So you gotta remember like how they make ions. and that helps with electronegativity.
Okay.
That was a good tip. I've never like.
Yeah, I didn't. There's always that question of like which one's more electronegative, because if you look at the trends, like they're one away from fluorine, and fluorine's the most electronegative. So I think that's a really good thought. That's really good with the halogens. Okay, how does everyone feel about electron configuration? And we can do some periodic trend problems if you guys want to as well.
Do you guys know how to do the little arrow thing that Diego was doing?
Yes. Do you guys know how to do the orbital diagram boxes?
Yes.
Yes.
Okay, I got 2 yeses.
Come on, guys,
Once
don't let.
no, I'll go ahead and cover it.
Wait, I have a.
Can we cover it, please?
Sure.
Like, I need one example at least.
Sure, no problem. Sorry, it is chat. I'll leave you guys to chat unless if it's pertaining to me. Please tell me. Okay, so I'd say let's do one with a large number of orbital diagram boxes. Let's do iron. So for iron, first for electron configuration, I recommend, or for quantum numbers, sorry, I recommend you start off with electron configuration and then you move into quantum numbers. So it's my electron configuration for iron, if I'm doing shortcut.
Start with argon.
Argon. Mm-hmm.
And then it would be 4s2. And then 3d6.
Okay. And 3d6. Okay. So we always base our quantum numbers on our last one. So when doing that, so N, L, ML, and then MS. I love this board because colors pop so well. So what would be my N?
3.
4.
So, all right, I got 2 different answers, and the one of the peer leaders want to explain why we base it off 3D and not 4S.
Ooh, I got you. So the Pauli exclusion principle, we mentioned that a little bit at the beginning. Does anybody remember what that means? Or what the Pauli exclusion principle is?
So none of the numbers can be the same, like none of the quantum numbers at least.
Yeah, so none of the quantum numbers would be the same. But if you think about it, how many elements, I guess, has this 4s or 4-2 shell filled? Well, we got calcium, but we got all of these inside with the exception of like chromium and copper, these ones. But then you can also see the problems with that because chromium and copper also have the 4s1. So because of Pauli exclusion principle and how we're saying that no 2 elements can have the same number of electrons or the same quantum numbers, that's why we don't really base it on the 4s1 and we're really basing it on this last inputted electron. Does that make sense?
Yes.
All right. Thank you, Jonathan. Okay. So now we know we're basing it on 3d6. So what would be my N?
3.
3. My L?
Is it 2?
SPD. Yes, it is 2. And then my ML. So ML, these last 2, these deal with the orbital diagram boxes, ODB. So how many orbital diagram boxes am I going to draw? And someone.
5.
Yes, I'm going to draw 5. 2, 3, 4, 5. And we know that because why? Why do I know I'm going to draw 5?
There's 10 electrons for each G.
Mm-hmm. And then what numbers am I going to assign to my boxes? From what range?
-2.
Mm-hmm. -2 to 2. So -2, -1, 0, 1, and 2. Okay. And then when I fill them out, how am I going to fill it out?
You put a positive arrow in each orbital first.
Yes, fill up arrows first. So I would do how many? Would I fill all of them up?
Yes.
Yes, I would fill all of them up. So 1, 2, 3, 4, 5. So fill up arrows first, and then what do I do?
You put the one you're missing in the first one.
Yes. So fill your down arrows. Next. So I'm going to do that. Down. Okay. So we based it on our last electron that we placed. So what will be my ML?
-2.
-2. And then my MS?
-1/2.
Yes, -1/2. Awesome.
Ooh, I'm going to jump in here for a
Go
quick.
ahead.
Okay, so the quick way that I do it is I kind of split the what's it called, the orbital or the shell in half. So I split it in half, and then I just number it them right there. So that's -1, 0, 1, -1, 0, 1, right? And then same thing here. Remember how we fill up the first from right here? We filled up that -2, -1, 0, 1, 2, and then we would do the down arrows again. -2, -1, 0, 1, 2, right? And because we split it in half, we can do the positive and negative 1/2s, right? So remember, because we filled out that positive 1/2, if it's on the left side of that little half that we made, that's going to be positive. If it's on the right half, then that's going to be negative. And then so from here, you can just see that it's kind of like playing Battleship, or I think that's the name of the game, where you go, oh, -2, -1/2, and then we're at iron. Right, so -2, -1/2, we're at iron. That's a quick way without having to draw the orbital box diagram. But again, it's the same thing, right? Because we're filling up, 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 and then down, 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 down. So, I mean, if you want to think about it that way, it might help you. Yeah, if you want to use Diego's way, that's also
Yeah. There's different ways. There's orbital, much like how we did electron configuration. There's the periodic table way, and then there's also the graph, the graph that we did. I'm sorry. Go ahead.
Can you repeat, like, how can we tell if it's positive 1/2 or negative? It wasn't clear.
Do you want to with Jonathan's method or with the orbital diagram method?
Whichever one is fine.
Okay, so I'll explain orbital diagram and then I'll explain Jonathan's. So for the orbital diagram, it's based on your last electron. So the last electron we placed was downward because we filled all our up arrows first, and then we fill our downward arrows because that's the last one we were missing. So we determined if it's positive or negative based on that one. So since it's downward, if it's downward, that's -1/2. If it's upward, it's positive 1/2. And then for Jonathan's method, his actually utilizes the periodic table. So he assigned positions to each, oh shoot, it's 2, sorry. He assigned positions to each square, and then he does it again. So it's up, -1, 0, 1, and 2. And then this whole square would be -1/2, and then this whole square would be positive 1/2. So since iron sits, let me go ahead and erase some of the lines because they're very distracting. So since iron sits in that -1/2, and then the position of iron is -2. So it's kind of like a grid. So that's how we knew it was -1/2 and -2.
Thank you.
No worries. All right, we're running out of time. So if you guys have any other questions, go ahead and ask. I'm actually going to be leaving soon. And then you guys will start working on those structures and module 14 as well.
Any other last minute questions? More example requests, anything?
I stop recording this section and leave the recording to somebody else.
Can you do like one example on page 237? Like where you have to find the element, or where it says if where you put impossible or possible.
That one. Okay. Does someone want to cover that one? I'll stop sharing.
I can do it, I think.
Okay.
All right, let's go.
I'll let you go ahead and share.
All right, let's go. So 237, number 13, right?
Yes.
Okay, so some of you might be familiar with this already because this is your homework. But essentially what you need to do here is you need to identify which one of these have quantum numbers that are impossible, because all the quantum numbers have a range. They can only be certain numbers, and if they're not those certain numbers, then they're completely impossible. They're 1, 2, 3, 4, 5, 6. Okay, so let's go. So for n, what are the possible values? Let's go first with what the possible values for each of these are. So for n, what are the possible values?
1 through 7.
1 through 7. So 1, 2,
Why?
4, 5, 6, 7. Any of these. Why are they possible? Why are these the possible values?
What does n represent?
Energy level.
They're the energy levels, right? So most of these energy levels usually correspond to they correspond to a shell, right? Or sometimes you can even consider it, they correspond to a period. So you have 1, 2, 3, 4, etc., right? So these are all the shells. Those are the...
How many periods does the periodic table have?
7.
7, right? So how many n values what are the n values that we can have if n means the energy level and we get the energy level from the periods on the periodic table? Did that make sense? No? Okay, well, it's 1 through 7 because there's 7 periods on the periodic table, right? And n represents the period
up to now, right?
Where it's found.
Up to now, right? Because the periodic table was designed to be predictive. So if we discover an 8th shell, then that's also going to be a possible value. But that'll probably be in a long time. All right. What about?
Sorry, Karina.
Oh no, you're good. You're good. You're good. All right. So what about L? What about L?
It will be 0 and then 1, 2, 3.
1, 2, 3, etc. These could be any of the possible values, right? But specific. So what is the relationship of L with respect to N?
L is n minus 1.
Is it only n minus 1?
Also n minus 2 if you're looking at F subshell.
Not quite. I mean, it can, yeah, right? It can be, but, okay, I'm gonna start again. So yeah, it can be n minus 2 if it's the F subshell, but generally it's any number, it's any number equal or less than, so this means equal or less than n minus 1. So it can be any number n minus 1. So for example, if you have L equals 2, what are the possible that's L. If you have an n equals 2, what are the possible values for L?
1.
1 and what else?
0.
0, right? So you could have either, so this 1, what shape does it represent? What kind of orbitals do these represent?
P.
P orbitals and 0?
S.
S, right? So you can have either P or S orbitals if you have an n equals 2. So just keep that in mind. Try not to answer with 1, 0 if you're not asked what are all the possible values. If you're looking at, we'll get to that in a second. We'll get to that in a second. Okay, so what are the possible values for m sub L? What's m sub L again?
The orientation.
Orientation, right? So orientation. I forgot to mention that L was the shape. Okay. So then if m sub L is the orientation, what is it related to? What are the values related to?
They're related to L, and
L,
they
right?
can be minus L to plus L.
Minus L to L. So, so for example, again, let's go again with, let's say we have L equals 1. What are the possible values for m sub L?
1, 2, plus 1. I mean, -1, 2, plus 1.
-1 through +1. So -1,
0, and then
0, and 1, right? Okay, does that make sense so far for everybody?
Yes.
Okie dokie. So last one, what's the last one that we're still missing?
the spin.
The spin, right? So that's, which one is that?
M sub S.
M sub S, right? So, okay. So what are the possible values for m sub S? This is the easiest one. I think this is the easiest one.
It's either plus or -1/2.
Plus or -1/2. Okay. So this one should be easier to identify when you guys are trying to figure out whether or not those are possible values, right? Okay, so I'm gonna leave this table so you guys can answer me now. We're gonna go over all of the ones on page 237. I'm not sure, I can't remember who asked for this one, but we're gonna go through all of these and everybody's gonna answer me whether or not these are possible and why. So the first one is 0, 2, 1, 1/2. All right, guys. So based on what we already talked about, is this one possible or impossible?
Impossible.
Possible. Why is that?
L is greater than N.
Right. L greater than N, and that's completely impossible. We can't have L is never bigger than L. In fact, it's never even equal to L. So just be careful to that. What other reason is this impossible to? What other reason do we have that this is impossible?
There's no energy level that it's 0.
It's, yeah, the energy level is 0. So is a 0 energy level possible?
No.
No, right? Starts from what to what?
1 to 7.
1 through 7. Well, in the case of so far, right? Up until now, we know that there's 7 energy levels. Okay. What other reason do we have what other reason do we have? So if L is impossible, is this if L is already impossible, then what does that leave m sub L? Is m sub L possible? Well, no, right? It's completely impossible. This is also impossible automatically. If this is impossible, the rest are already impossible. So, any questions so far?
No.
Let's go over to the second one. So 2, 0, 0, and 1/2. Okay, so just remember this is N, L, m sub L, and m sub S. Okay, guys, is this one possible or impossible? What do you guys think?
Possible?
It's possible, right? So why do you guys think this is possible?
Well, L is less than N,
Mm-hmm. L is less than N.
and
Okay.
ML equals L.
Mm-hmm. Okay, well, yeah, right? Because in this case, if you have L equals 0, then obviously your only value for M sub L is going to be 0, right? What about the spin number? Is that good? We good with this? Are we Gucci?
Wait, I have a question.
Yes.
So wouldn't it also be for L1? Or is it not always?
So it's not always L. L is not always 1 if you have 2, because remember, the L's represent, so if we have N equals 2, the possible numbers for L are either 1 or 0. So you can't have multiple L's for this one. It can be either or 1 or 0. So this is definitely a possible number.
Okay.
So so in this case, if we have L equals 0, what shape is that? What kind of orbitals do we have in there?
S.
S orbitals, right?
The S.
Right. So that's definitely
Oh,
possible.
okay. I see your point now.
Yeah. So this is definitely possible. It can be either 1 or 0. So don't worry about it. And the spin, is this good? Are we good on the spin?
Yeah, because it can either be a half or minus a half.
Yes, sir. Absolutely. So this is possible. Right. So we Gucci on this one. Okay. Let's go on to the third one. So it's 2, 2, 2, and 1/2. So let's look at this one. Is this possible or impossible?
Impossible.
Possible.
Okay. Oh, one of you guys said, did both of you guys say impossible, or did one of you guys say possible?
I did say.
I said impossible.
Okay, one of you guys
Yeah,
said.
I said impossible.
Okay, so
No,
why is it impossible, guys?
Because L is equal to N.
2.
L equals to 2, and what do we say about L? What kind of values can L have?
Has to be less than N.
Less than N, right? So any number equal to N minus 1 or less than that. Okay, so this is impossible. Okay. Any questions so far? Are we good?
Yes.
Okay, let me see the chat. No questions. Okay, cool. Let's go on to let's go guns blazing to the next ones. All right, what about this one? Just look at it and let me know if you guys can tell me if it's possible or impossible. I wish I could make polls here, but apparently I can't. So.
Possible?
All right, possible. I got one possible. I got one possible in the chat. Everybody agree with it? Okay, guys, just remember, don't let others talk over you. This is why America is the way it is. Just kidding. Okay, it is possible because we have N, we have L. It's N minus 1, so it's 4 minus 1, that's 3. So this one's good. And is 0 one of the possible numbers for M sub L? Brianna says yes. All right. Yes, so it is. So 0 is one of the possible numbers, and we have 1/1/2, positive 1/2. So this one's definitely possible. So this whole configuration is Gucci. Gucci. Okay, if I'm going too fast for you guys, just let me know. Slow down. Just open up your mic and be like, "Hey, slow down," or tell me to speed up. It doesn't matter. Just, hey, it's like, hey, we got a tight schedule here. Okay, cool. Let's look at this next one. Look at it real quick and tell me, is it possible or impossible?
Impossible.
Impossible, right? I got one impossible. I got another impossible in the chat. Another impossible in the chat. Okay, everybody agrees it's impossible. What is impossible about this about these quantum numbers here?
Well, if L equals 0, ML has to be equal to 0.
Right? Exactly. So this M sub L is wrong. So M sub L can only be negative L, 0, or L. So this is impossible, impossible. It's a travesty for it is a travesty for our eyes. Okay, I'm gonna stop. Okay, let's look at the last one, very, very last one. Tell me, is that possible or impossible?
Impossible.
Impossible.
Got it. I got 3 impossibles at the same time. All right. Why is this impossible, guys? I got 4 impossibles. Okay,
Because
L
is bigger than N.
L is greater than N. Exactly right. So L greater than N, and that is absolutely unacceptable. You guys ever watch Adventure Time and you remember this guy named Lemon Grab and he would go, unacceptable, or something like that? Like that. That's how we feel. That's how we feel. We do not stand this. We cannot stand for this. We don't stand. It's canceled. All right. So how you guys feel about this little exercise about quantum numbers, how to know whether or not they're acceptable or not? You guys feel good, confident?
Yes.
Good, strong.
Thank you for explaining it.
All right, no problem. Okay, you guys are good, strong, and smart people. You guys got this. Okay, so I'm gonna stop sharing my screen for a second. Does anybody need this? You guys can screenshot it if you want. Going once, going twice, and going, and gone. Okay.
So,
Oh no, sorry. You can keep going, Sylvia.
I was just making a dumb joke. It's solved.
All right. So does anybody have any last questions about module 11 before we move on to, is this 13 we're going through? Okay.
Yeah, we're moving on to 13.
Andre or Alan, if you guys want to take over, or I don't know. Unless Corina wants to keep going.
I mean, I can keep going with the strictures, but I don't know if you guys, because you guys have been quiet.
No, I can take on module 13. That's okay.
All right,
so
Alan.
here, let me quickly share my screen. So basically, it's
Hold up.
structures.
I'm not sure. I think I was recording, so I'm gonna stop the recording, and I want somebody else to start recording because this section has already gone pretty long. So